For part 2, we're going to talk about inferences for regression. Early in this course, we determined how to fit a regression line to a set of data. So you have a scatter plot and you want to fit a line to that data for the purpose of description and prediction. However, when we compute the linear regression coefficients, particularly the intercept and slope, because those are the simple linear regression coefficients, based on a random sample of data from a population, how do we know these coefficients are just due to random sampling variability? How do we know that these coefficients aren't just an artifact, that in fact the population intercept and slope, how do we know that those have any kind of relationship to the sample intercept and slope? Well, just like correlation, we can make inferences about the population coefficients using the coefficients from a random sample from that population. So let's review simple linear regression. Recall that if we have a population, we will use Greek letters to write out the equation for simple linear regression. The idea is that we have an outcome y, and we say it's a function of a deterministic component and a stochastic or random component. So you have the y hat, the predicted values of our outcome, plus this error term, epsilon. That equals the intercept plus the slope times their x variable plus the random error term. If we have a sample, then we will use Latin or Roman letters. Right? The idea is that we want to go from these Latin or Roman letters to these Greek letters. We want to say something about this population regression model based on a sample regression model. The idea is that we don't observe the intercept and slope in the population, but we can make inferences about them. So let's look at this cricket chirps example revisited. All right, this is our cricket chirps data set. This is based on the insight, the claim from long ago, from the 19th century, that you can use cricket chirps per minute as a farmer's almanac type thermometer. The idea is that you can predict temperature in Fahrenheit or Celsius based on cricket chirps per minute. So each row here, it's a different observation at some point in time. So the idea is you've gone out into the field 7 different times and you've calculated the temperature using a real thermometer, and you've calculated the cricket chirps per minute. And we want to use this data set of observations to create a regression model, a simple linear regression model, that will allow us to use cricket chirps to predict temperature in Fahrenheit. So we've counted the number of chirps per minute and the temperature. We're going to call y temperature in Fahrenheit, and then we're going to call x the number of chirps per minute. So for our cricket data, we can find the intercept and slope using a simple linear regression model fit to the scatter plot of data, and we obtain these coefficients. We find that the sample intercept is roughly 37 degrees Fahrenheit. So when cricket chirps is 0, the expected mean temperature is about 37 degrees Fahrenheit. Then we find the slope is 0.23. For every 1 unit increase in our x variable in cricket chirps per minute, we expect the temperature to increase by 0.23 degrees Fahrenheit. The line we can succinctly express using these two numbers, the intercept and slope in the sample, so that our predicted values of y equals 37 roughly plus 0.23 times x, where x is cricket chirps per minute. This is what our model looks like when we fit that line that we just described onto the scatter plot of data. Any point on this line, it's given by our values of y hat. The intercept is when x equals 0, so when cricket chirps equals 0. And then the slope is simply the rise over the run. You can take any point on the line, you can move over to the right, and then go up to the line again, and the ratio of the rise over the run, that will give you the slope. Typically, we make it so that the run is 1, and then the rise is just going to be the coefficient from the output, which is roughly 0.23. That just aids interpretation. So we can say that the slope in the sample is 0.23. So this is a summary of simple linear regression. We have intercept, we have a slope, we have rise over run, we have a simple equation that conveniently describes the entire line using 2 numbers. And then we also show here our underlying data set. Now the thing is, suppose that these 7 observations, suppose they're random samples. These are random draws from some population of possible observations. The idea is we want to use that sample to say something about the population.